In this episode, we're going to talk about a pair of technologies that often sit quietly in the middle of OT environments, moving data between systems that were never designed to speak to each other directly. When beginners first hear about OPC, they sometimes assume it is a single protocol like the ones we discussed before, but it is better understood as a way to standardize data exchange so different devices and software platforms can interoperate. That interoperability is valuable because OT environments are rarely built from one vendor and one generation of equipment, and organizations need a practical way to share process data with operator screens, historians, analytics tools, and even business systems. The two major families you will hear about are OPC Data Access, OPC DA, and OPC Unified Architecture, OPC UA, and the differences between them matter for both security and operational reliability. This lesson is about understanding what these technologies do, how trust works when data crosses boundaries, and how to think about safe use without turning the conversation into tool-specific configuration. If you can keep a clear mental model of what OPC is trying to accomplish, you will be able to reason about common risks like unauthorized access, misleading data, and overly broad connectivity. You will also be able to spot when an organization has built a useful bridge and when it has built an unnecessary highway into sensitive networks. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good foundation is to understand why OT environments need interoperability in the first place, because the need is not optional. It comes from real operational pressure. Operators want a single view of the process even when different parts of the plant use different controllers and different communication methods. Engineers want to collect data for troubleshooting and optimization without rewriting every device interface. Historians and reporting systems want standardized access to values so they can store and trend them consistently. When systems do not share a common data model, every integration becomes a custom project, which is expensive and fragile, and fragility becomes a risk when systems must run reliably. OPC emerged as a way to create a common approach to data exchange, particularly around tags, so that applications could read and write values without needing to know every vendor's internal details. Beginners should notice that the value here is not only convenience, but reduced complexity, because complexity is a major driver of both outages and security gaps. At the same time, interoperability creates pathways, and pathways create risk, because data exchange that is too open can allow unintended access or manipulation. So the safe use of OPC is really about balancing useful integration with disciplined trust boundaries. OPC Data Access, OPCDA, is one of the older families, and it grew up in an era where many OT systems were built around Windows-based components and local, trusted networks. The key beginner idea is that OPCDA is typically used for real-time data exchange between an OPC server that exposes processed data and an OPC client that consumes it. The server here is not necessarily a giant enterprise server. It is the component that makes data available, and the client is the component that requests or subscribes to that data. OPCDA is often associated with classic industrial setups where HMIs, historians, and applications connect to an OPC server to get access to controller tags. Because of its history, OPCDA environments often rely heavily on the surrounding operating system and network environment for security, rather than on strong security mechanisms built into the data exchange itself. That means trust is often implicit, based on being on the right network and having the right system permissions. Beginners should understand that implicit trust can be fragile when environments become more connected, because it assumes the network is closed and controlled. If that assumption weakens, the exposure of data and control capability can expand quickly. To understand OPCDA risk, it helps to think about what happens when data exchange becomes a bridge between zones that were previously separated. An OPC server might sit close to the control environment, collecting data from controllers, and then provide that data to multiple clients, some of which might be in less protected networks. If the server is configured to allow both reads and writes, the bridge can carry control influence as well as visibility. Even when only reads are intended, the reality is that broad access to real-time process data can still be sensitive because it reveals operating conditions, equipment states, and sometimes patterns of production. Another risk is that if a client is compromised, it can use its trusted position to request data or attempt actions the attacker could not do directly. Beginners sometimes think of a server as a strong protective layer, but a data broker can become a concentration point where many trust relationships converge. Concentration points are valuable because they simplify integration, but they also become high-value targets because compromising one can provide access to many streams. Safe use starts with understanding this role clearly. OPC components are not just connectors, they are trust hubs. OPC Unified Architecture, OPC UA, was developed in part to address limitations of older approaches, and the beginner-friendly way to think about it is as a more modern framework for interoperability with a stronger security story and a richer data model. OPC UA is designed to support platform independence, meaning it is not tied to a specific operating system in the same way, and it is designed to carry structured information in a way that supports more consistent understanding across systems. It also includes concepts for authentication, authorization, and encryption in ways that are more aligned with modern secure communication expectations. The exact mechanisms can be complex, but you do not need to be an implementer to understand the idea. OPC UA is built to support trust decisions explicitly rather than relying entirely on the assumption of a trusted local network. This matters because OT environments increasingly include remote access, cloud analytics, vendor support, and enterprise integration, and implicit trust becomes less realistic in those conditions. Beginners should also understand that more secure capable does not mean secure by default, because even strong frameworks can be deployed poorly. OPC UA can still create overbroad pathways if access is not restricted and if trust decisions are made casually. The core security lesson is that the technology supports better trust control, but the environment must actually use those controls responsibly. Interoperability always raises the question of trust in data, because if you are making decisions based on a value, you need to know whether the value is authentic, timely, and accurately mapped. In OT, a small mapping error can be dangerous, such as a display showing the wrong tank's level or a report associating the wrong sensor with the wrong equipment. OPC systems often handle large numbers of tags, and tag naming conventions can be complex, so the chance of misconfiguration is real. Another trust issue is freshness, because data might be cached, delayed, or updated at different rates, and an operator might assume a value is live when it is not. A historian might trend values that are accurate enough for analysis, but not appropriate for immediate operational decisions. Beginners should recognize that trust is not only about whether the channel is encrypted, it is also about whether the right data is being delivered to the right consumer with the right expectations. Security and safety both depend on this, because incorrect trust can lead to wrong actions. This is why mature environments treat data exchange as part of system integrity, not merely as convenience. When you see an exam scenario involving interoperability, think about whether the system has controls to ensure correct data mapping, appropriate permissions, and consistent handling of updates. A related topic is the difference between read access and write access in OPC contexts, because OPC can be used to expose values for monitoring, but it can also be used to send commands or change values. In many environments, the safest starting posture is to keep the exchange focused on read-only visibility unless a clear operational requirement exists for writing through OPC. Write capability can be useful, such as allowing a supervisory application to set a target or acknowledge a control action, but it increases risk because it introduces a control pathway that might bypass other safeguards. Beginners should understand that even if a write action is legitimate, the pathway can still be abused if access controls are weak or if credentials are stolen. Another subtle risk is that writes may happen indirectly, such as a client updating a value that is then used by logic elsewhere, meaning the influence can be broader than it first appears. Safe use, therefore, includes limiting which clients can write, limiting which values can be written, and ensuring that writes are logged and attributable. The goal is not to prevent all writes forever, but to treat right capability as high impact and deserving of stronger controls. Exam questions often reward the idea that visibility is usually safer than control when you are unsure, and that control should be explicitly governed when it is necessary. Because OPC often sits between OT and IT, it also becomes a natural place where segmentation decisions show up. A common pattern is to place OPC servers in an area that can access control systems while also being reachable by monitoring and historian systems. But that area must be designed carefully so it does not become a wide-open bridge. Beginners should think of segmentation here as designing a deliberate boundary where data can flow out in controlled ways and where inbound access is tightly restricted. Even without drawing a network diagram, you can imagine the principle. The closer a system is to direct control, the more carefully you protect it, and the more you limit who can reach it. OPC components near control systems should not automatically be reachable from broad enterprise segments, because that increases the chance that a compromise elsewhere becomes a compromise of the control environment. If an organization needs data and business systems, the safe approach is often to control the flow through curated interfaces rather than granting broad access to raw control data. This is also where governance matters, because decisions about who needs access and why should be made deliberately, not by convenience. For exam reasoning, when you see an interoperability solution, ask whether it respects boundaries and whether it minimizes unnecessary pathways. The best answers usually preserve necessary data exchange while reducing the chance of lateral movement and unintended control. Another critical aspect of safe use is managing identities and trust relationships, especially in environments where OPC UA is used with explicit security features. Trust often involves certificates or similar mechanisms that allow systems to recognize each other and establish secure sessions. Even if you do not configure certificates yourself, you should understand that this creates operational responsibilities like maintaining trust lists, handling renewals, and ensuring that trust is not granted too broadly. If trust is given to any device that asks, the security features become meaningless because the environment is still operating on implicit trust. If trust is managed too tightly without process, the environment can suffer outages when certificates expire or when legitimate systems are blocked unexpectedly. This is a classic OT theme. Security controls must be reliable and maintainable, not just theoretically strong. Beginners should understand that trust management is part of operating a secure interoperability environment, and it must be planned as a lifecycle activity, not a one-time setup. Logging and monitoring also matter, because secure sessions and access decisions should leave evidence that can be reviewed during troubleshooting or incident investigation. Without visibility into who accessed what data and when, trust becomes guesswork during an incident. Safe use, therefore, includes both preventive controls and accountability. A common beginner misunderstanding is treating interoperability as an unqualified good, assuming that more connectivity automatically means better operations. In reality, more connectivity can increase complexity, and complexity can create more failure points and more security exposure. Another misunderstanding is assuming that OPC UA automatically makes everything safe, when it actually provides capabilities that must be correctly used and maintained. Beginners also sometimes assume that if the data is being displayed, it must be correct, but display correctness depends on correct tag mapping, correct refresh behavior, and correct trust in the source. A subtle but important misconception is that security is only about blocking attackers, when in interoperability environments, security is also about preventing accidental misuse and misinterpretation. A misconfigured client that pulls the wrong data or writes to the wrong tag can create operational harm even without malicious intent. This is why procedures, change control, and verification are as important as technical mechanisms. The exam may present scenarios where the safest choice involves reducing unnecessary access, improving governance, or ensuring read-only access where possible, rather than simply turning on integration features. When you approach interoperability as a managed capability, not a free feature, you will make safer judgments. To close, using OPC data access, OPCDA, and OPC Unified Architecture, OPC UA, safely is about understanding that these technologies are bridges that enable valuable data exchange, But bridges are also points where trust must be defined and controlled. OPC UA often relies heavily on a trusted local environment and operating system-level assumptions, which can become fragile as networks converge and access expands. OPC UA provides a more modern framework with explicit security capabilities and a richer data model, but it still requires disciplined deployment, identity management, and ongoing maintenance to remain secure. In both cases, safety and security depend on trustworthy data mapping, appropriate handling of freshness and quality, and careful control of right capabilities that can influence the process. Interoperability should be engineered with segmentation and governance so that necessary data flows are supported without creating unnecessary pathways into sensitive control environments. When you can recognize OPC components as trust hubs, reason about read versus write risk, and appreciate that trust includes both authenticity and correct interpretation, you are well prepared for security OT plus questions that test judgment in real OT integration scenarios. This understanding will also support later topics where mixed environments and cross-system data flows are central, because you will already be thinking in terms of controlled bridges rather than uncontrolled connectivity.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.